So, we have been discussing about the product operator formalism of the density operator, which we wrote like this: summation Bs of T Bs, and then we looked at the various basis operators, these ones. For one spin we had a set of basis operators, there were 4. For 2 spins the basis operators number were 16. For 3 spins then we have a number is 64. This is 4 to the power whatever that is. So, this is 4 to the power 1, 4 to the power 2, 4 to the power 3. And we also had said that these are all products of angular momentum operators, and we also saw what these individual operators represent in the density matrix. Where do they represent? We have various kinds of single operators, and we also have operators of like this, which are products of 2 angular momentum operators, and we will also have products of 3 angular momentum operators, ILX, ILZ, IMZ, and so on so forth. So, these are some illustrations, and we saw exactly what these some of these individual operators represent for the 1 spin, 2 spin cases. Basically we looked at those which are representing in phase magnetization of single spin, and also for the 2 spins we looked at in phase magnetization in all the 3 cases of 1 spin, 2 spin, 3 spin cases. We also looked at the products of this type, that K, IKX, ILY, how they represent a mixture of double quantum and 0 quantum coherences, and by combination of more than one of such operators we can generate pure double quantum coherence or pure 0 quantum coherence. So, and these ones therefore they are present in the density operator. Looking at the density operator and looking at these ones, we can make an interpretation of what is the system, how the system is evolving through the pulse sequence, what kind of coherences are generated through the pulse sequence. This is the physical meaning of those. Calculation of the time evolution, we will come to it very soon. So, now continuing with this discussion, what sort of spectra we expect in the for the anti-phase magnetization in the 3 spin case, that is what we are going to see. Okay. So, now we consider the 3 spin example. So, the 3 spin example we represented as KLM, all the 3 are weakly coupled spins, and we saw earlier in the 3 spin case also for operators like IKX, ILX, IMX, what sort of transitions are occurring, how do we represent these transitions in the 3 spin system. Let us do a recap on the energy level diagram of the 3 spin case once more. We have 8 energy levels here, and these are represented as 1, 2, 3, 4, 5, 6, 7, 8. Essentially it is a duplication of the 2 spin case, and in one of these 4 energy levels you have the 3rd spin as M spin as in the alpha state here, and you see here this is all M spin is in the alpha state, and here in these 4 energy levels the M spin is in the beta state. So, that is how you generate the 8 energy levels, and the transitions accordingly are as K transitions and L transitions and M transitions. The ones which connect from this group to this group are all the M transitions. The ones which are in this group, they are basically the K and L transitions, and that is indicated here. So, they are indicated by different colors here. So, and therefore we can understand what these ones represent. The arrows indicate what sort of spectra you will get when you actually measure the spectra of the 3 spin system. And we have seen therefore in the earlier cases that we have in phase magnetization of the K spin, if one is trying to see, then you will have 4 lines which are in phase, and if we have similarly for the L spin and similarly for the M spin. So, now we are going to see if I have a term of this type in the basis operator. For the 3 spin case, remember for the 3 spin case also we have 64 operators. 64 operators will consist of single angular momentum operators, the products of 2 angular momentum operators, and products of 3 angular momentum operators. Now we are going to consider a 2 spin product for a 3 spin system, and this is the operator like 2ikx ILZ in a 3 spin system. What does this represent? So it will be very similar to what we had in the 2 spin case itself, that we will have these 2 transitions. There is one transition, this is the K transition, alpha K is going to beta K, this is the K transition, and correspondingly this is the K transition, alpha K to beta K. But now you see the arrows. In this case the arrow is like this, and in this case the arrow is like this. So this represents an anti-phase term. These 2 terms will have opposite signs, and that is indicated by kind of a representation here. If 1 3 is positive, then the 2 4 transition is negative, okay, and that will be in this block. The same thing will happen in this block as well. 5 7 and 6 8 will also have opposite signs. If this is 5 7 is positive, 6 8 will be negative. So therefore we have here 5 7 transition and 6 8 transition. The separation between these 2 will be the coupling constant between the spins K and L. The same thing is here, okay. Of course the separation between these 2 or these 2 will be the coupling constant of spin K with spin M. So you have therefore a doublet of a doublet, and you can see here the antiphase nature is for the coupling of K and L, whereas if you look at these 2 peaks which arise as a result of the coupling between K and M, they are in phase. So therefore with respect to the M spin, these 2 are in phase. This whole doublet has the same sign as this doublet, okay. This is negative positive and this is negative, the same sign pattern here for this one and this one. So therefore we call this as the K magnetization, which is antiphase with respect to L but in phase with respect to M. Let me repeat that again here. So we have here 4 lines. The 4 lines come as a result of coupling between K to L and K to M, and we can represent here the same in a slightly different notation. I can write that here itself. So let us say I have one line for the K spin in the absence of any coupling, then I will have here 2 lines as a result of coupling JKL, and let me represent this as plus and minus, because I get, because of the K in this system, we will have the 1 3 transition and the 2 4 transitions have the opposite signs. Now there is a Km coupling subsequently. So Km coupling results to splitting like this, then we will have situation like this, then we will have this one, we call it as plus plus here and minus minus here, and this is Km coupling. So in this case I have assumed that the KL coupling is larger than Km coupling, but you can also have a situation where Km coupling is larger than the KL coupling. So in that case what one could also do is we have this here, then we have these 2 as the result of the KL coupling, and then we will have a splitting again due to the Km coupling, then we will have this sort of a situation, okay. So this then will be plus minus, this will be plus minus, because this is plus and minus, this splits into 2, when then it will give to the minus minus here, and this plus splits into 2, then we get plus plus here. So this is the kind of a situation what you are seeing in this diagram. So this is what you are seeing in this diagram. We have these 2 transitions are shown here as plus and minus, that is this situation, and this is plus minus and plus, whatever that is, you may call this plus, this minus, or vice versa, does not matter. So you get different kinds of patterns depending upon the relative magnitudes of the coupling constants. So here we have assumed the Km coupling is larger than the KL coupling. The KL coupling is resulting in this kind of antiphase peaks which are positive and negative here, and this is antiphase peaks, and these peaks are in phase because this is due to the Km coupling. If this is positive positive or negative negative, and this is negative negative or positive positive correspondingly. So therefore this is the way you get for Kx Lz in a 3 spin system. If you were to take KYLZ in a similar situation, you will get the same sort of pattern in both these cases, but they will have dispersive line shape because of the KY term. If I take a KY term, it will have a dispersive line shape. So similarly, for if I were to take LYMZ or MYLZ, so accordingly one will have such kind of patterns in the individual multiplets of the L and the M spins. So this is an illustration to show how the different transitions appear in your spectrum. Okay. Now let us consider a further extension of this. We will consider 3 spin product. A particular example I have taken here is the 3 spin product IKX, IMZ, ILZ. 4 IKX, ILZ, IMZ. Notice here the transverse is only for the K, whereas the L and the M spins are along the Z axis. Therefore, these ones, this term obviously represents the K magnetization, because whatever is in the transverse plane is what we observe, and we call that, it represents that magnetization. So this is the K magnetization. Now we can intuitively we can think that this is something which is antiphase with respect to both the L spin as well as the M spin. So what do we expect here? So in this situation, earlier this group had the same sign as this group. If this is negative positive, this is also a negative positive, that is because we had the in phase character with respect to the M spin. Now the K magnetization in this situation will be antiphase with respect to M as well. Therefore, the first antiphase term appears because of this, the KL splitting, and secondly this whole term is inverted because of the antiphase nature with respect to the M spin. Therefore, this now which was negative here now becomes positive, and this one becomes negative. Therefore, you get a pattern here, this is negative, positive, positive, negative. Okay. The coupling constant here is of course, then this is the KL coupling, and from here to here that remains the KM coupling. Okay. Now you see, if you look at the splitting due to the KM, it is one line here, another line here. Now these two are having opposite signs with respect to each other, and therefore this is antiphase with respect to the KM splitting as well. So it is antiphase with respect to the KL splitting, this is negative positive KL splitting. It is also antiphase with respect to the KM splitting if this is negative and this is positive. Similarly, this and this have opposite sign. Therefore, we call this as antiphase magnetization of K with respect to both L and the M spins. So in the diagram here you can also see, if I take this as positive direction here, this as a positive negative direction here, and then correspondingly I will have this as negative direction here and this has a positive direction here. The same thing is represented schematically. This is the schematic representation of how the peaks will appear in your spectrum when we record, when your density operator contains this sort of a term. This term sort of a term is a basis operator present in your density operator. Then if you were to measure this, then you will get a spectrum which will produce a spectrum like this. This particular term, of course various other terms will produce different kinds of spectra. So we are interpreting what are the contributions of the individual basis operators in your NMR spectrum. Okay. So therefore, so much for the physical meanings of the individual basis operators, what do they represent in your NMR spectrum. But now we come to the next objective, that is we must be able to calculate the evolution of the density operator consisting of all of these basis operators through the pulse sequence. Again repeat this slide here, this slide you have already seen before. This is a multi-pulse experiment with so many pulses, and the system is evolving with the time, starts with the time 0. We have this pulse here and H1 tau 1 pulse here, then evolution under free precession for the Hamiltonian H2 tau 2, then P3 H3 tau 3 P4 and so on and so forth. So for free evolution we have to calculate the evolution under the Hamiltonian, this is for these ones, and then for the pulses we have this evolution under the pulses P rho P minus 1, and rho here can be a summation of all the basis operators, and this is the same equation what we had earlier. Start with rho 0, keep applying the pulses and the evolution under the various Hamiltonians as we have discussed before. Okay. So now we explicitly put this basis operators here for the free evolution. I call this as rho dash. The rho dash is summation Bs e to the minus I by h cross h t Hamiltonian t, then you have this basis operator Bs e to the I by h cross h t, and for the pulses we call it as rho double dash, then this is Bs p Bs p minus 1. This is the constant, therefore this can be taken out, and we have this pulse here p, Bs and p minus 1. The basis operator set for single spin, we have this expression, and all the multiple spins are also constructed from these individual angular momentum operators as I mentioned before. Now let us go further and try and calculate the evolution under the Hamiltonian and evolution under the pulses. What happens when you apply the pulses, what happens for when the density operator evolves under the Hamiltonians. Now let's write the Hamiltonian once more here. Explicitly we will write the isotropic Hamiltonian for weakly coupled spin systems in liquids consists of two terms, and this is the Zeeman term where it is due to the interaction between the nuclear magnetic moments and the magnetic field, and this is represented as omega k Izk summation over k. The k is the index which goes over the various spins. So we can write as kz or zk, does not matter, earlier we used kz here, but does not matter, it means the same thing, we are referring to the same thing. This is the precessional frequency of the k spin, and this is the coupling constant term where we have jkl is the coupling constant, and the operator term for the interaction is Izk, Izl, or you may call it as Ikz, Ilz. So it is the same thing, just the indices are changed here. So we could have written it as Ikz, Ilz as well, same thing. And in briefly we write it as Hz plus Hj. Okay, this is the coupling Hamiltonian, this is the Zeeman Hamiltonian. The first term represents the chemical shifts and the second term represents the scalar couplings. Okay. For evolution of a basis operator Bs, obviously we can write this Bs prime, this for the rho prime I write it as Bs prime now because we are considering the particular operator Bs here. So Bs prime I write it as e to the minus Iht Bs e to the Iht. Yeah, is a very simple extension of the previous equation. For H now I write explicitly e to the Ihz plus Hj t Bs e to the I Hz plus Hj. So basically putting for H here summation sum of the Zeeman and the coupling terms. Now for the weakly coupled spin system, you remember what the Hamiltonian consisted of. So Hamiltonian consisted of Ikz term here and Kz Lz here. So these are all Z components. The Z components, therefore this part of the Hamiltonian commutes with this Hamiltonian because Kz operators, the Z operators, they all commute. So and they all belong to the same spin. So therefore these two will commute. So when we do that, then of course we can actually calculate the evolutions of these operators separately without affecting the result in any manner. So if I were to write explicitly this, I can write this Hz plus Hjt as Hj plus Hzd, it does not matter because this only means there is an order of the evolution, order of the calculation is going to be interchanged. So here I keep the same Hz plus Hj, this is Hz plus Hj, and this part I turn it in the reverse manner, I write it as Hz plus Hzt. What is the consequence of this? For the Bs prime I will have evolution under the Hzt I can calculate this, therefore this will be e to the minus Ihzt Bs I to the Ihzt and multiplied by e to the minus Ihjt on this side and on this side e to the Ihjt explicitly. The central term will represent chemical shift evolution, right. So let me write that explicitly here. So I write it as Bs e to the minus Ihzt e to the HZT, and then here it is e to the minus I HJT T and e to the I HJT. So this particular term here, this is the chemical shift evolution, right, and from here to here, this after that this will be the J evolution. So we will first calculate what is the chemical shift evolution of a particular basis operator Bs. So for this we take an example of IKX. Let us say Bs is equal to IKX and we will calculate the chemical shift evolution, that is under the influence of the Hamiltonian Hz. So the Bs prime will be e to the minus I omega k Izk Ikx e to the omega k Izk t. Of course you be careful that somewhere I have used this Zk and then Kz and they get mixed up here. So here I have used Kz here and here it is Zk. So essentially I am meaning the same thing, okay. So this will be e to the minus omega k Ikz t Ikx e to the I omega k Ikz t. We have previously derived this formula, e to the I minus I beta Ix is given by this expression cosine beta by 2 minus 2I Ix sin beta by 2. This expression we have derived earlier by explicitly expanding this exponential function as a series, and then we figured out that this can be represented in a simple manner like this. So we will use the same trick here. So we will write explicitly this one in the form of this kind of an equation. So Bs prime will be cosine omega k t by 2 minus 2I sin omega k t by 2 Ikz here, that is this, and then I have this Ikx, it is this, and then I have this for the other side I have cosine omega k t by 2 minus 2I sin omega k t by 2 Ikz. So let us explicitly calculate this. We get here cosine square omega k t by 2 Ikx, this one will give me cosine square, this multiplication will give me cosine square omega k t by 2 and Ikx will stay here, and then this product, notice here I should have here a plus sign because this is e to the I omega k zk, yes. So I should have here a plus sign. So and then I will have here this product. So this term with this term gives me 4 sin square omega k t by 2, because this is minus 2I and plus 2I gives me minus 4I square, that is plus 4, okay, and sin square omega k t by 2, but these operators I cannot move around, I have to keep them here, Ikz, Ikx and Ikz. So these ones will stay here, okay, these do not commute and therefore I cannot move them around, okay. And then I will have here two terms of the cross term, one due to this and the other one due to this. This gives me minus I sin omega k t, a commutator of Ikz comma Ikx. The two terms clubbed together can be represented in this manner. So I have a commutator here Ikz Ikx. Now here we have to calculate what this the 3 product term implies. So we have here Ikz, Ikx, Ikz. What does this imply? So let us try and calculate that using this matrices once more. I have put here Ikz is half 1 minus 1 and Ikx is half 0 1 1 0 and Ikz again is another half 1 0 0 minus 1. So you put these 3 matrices, because this is the k spin I can simply take the product. Notice all of these belong to the k spin. Therefore I can simply take the product here and this gives me minus 1 by 4 Ikx. Okay. So therefore that 4 cancels, then I will get here cosine square omega k t by 2 Ikx minus sine square omega k t by 2 Ikx plus the last term, this one remains, this one is there, and this gives me Kz Kx, this gives me Iky, okay. So this commutator gives me Iky. So therefore what I get here Iky, and because of the I minus I square, so I get plus, therefore I get here a plus sign minus omega kt ky. Therefore, what I got finally, cosine omega kt ikx plus sine omega kt iky. So, after all this calculation, what we have got is ikx as a result of evolution under the ikz Hamiltonian, I get these two terms. See, if I went to write here a simple manner as in a symbolic form, ikx under the influence of the Hamiltonian hz gives me, it simply means a rotation, gives me ikx and omega. So, I write to represent this in a pictorial manner like this. Let us say we draw the 3 axes. The 3 axes we label them as ix, iy and iz. Of course, it can be, is a very general thing here, it can be k spin, l spin, whatever it is. So, it just represented as x, y and z, and this represents the Hamiltonian part. What the circle here implies, this is the Hamiltonian, and I have the transverse magnetism, this is the basis operator here, kx here, the basis operator, and under the influence of the Hamiltonian, this is the time evolution that is going on, this rotates in this manner, right. So, after a certain time t, if your rotation is here, then I have a ikx cosine omega kt plus iky sin omega kt, right. So, that is, so this represents a rotation in this manner. So, you can extend this argument further to say that if I were to take a iky here, suppose it were iky, the same rules will apply. So, this represents the full rotation of the entire magnetization components. So, if I were to start from iky here, then after a certain time tau, if the magnetization has rotated like this, then what I would get out iky cosine omega kt iky, because this will be cosine, this if this it has rotated like this. So, therefore, I will have this component cosine omega kt iky and minus ikx sin omega kt in that case. So, if I were to write for the iky, let me also write that here. So, if I were to start with iky, then this will go iky cosine omega kt minus ikx sin omega kt, right. So, that represents the rotation of the y magnetization from here to here, right. So, therefore, we have derived this principle to how this evolution can occur. So, we stop here.